Hello and welcome to this episode of Physical Attraction. This one's called the National Almost Ignition Facility. When we last left the National Ignition Facility, the laser had just been switched on with some degree of fanfare, aiming to start its ignition campaign. The banners at the opening day ceremony said, "Bringing star power to Earth." The scientists closer to the project said that there was plenty of room for nasty surprises. So what exactly happened in NIF's ignition campaign? Let's find out. Progress on the initial campaign at NIF was limited by a few factors. First off, of course, there's still the whiff of secrecy and classification around what is close to a weapons research facility. There's also the fact that you can only fire so many laser pulses, perhaps one or two a day. Essentially, this arises due to the fact that you have to allow the apparatus to cool down before it can be fired again, or risk melting vital components. At the height of the campaign, they achieved 57 shots a month, around 2 a day, which of course means that data collection is inevitably slow. But improvements were being made. The first few test shots appeared to be just 0.1% of the way towards ignition, but over the course of a couple of years, this would be improved by a factor of 100 on the same device. Remember the triple product for plasmas of confinement time, density, and temperature? We used it to explain the difference between laser fusion and magnetic fusion. Magnetic fusion goes for long confinement times at lower densities and temperatures, while laser fusion aims to, very briefly, achieve much higher densities and temperatures. A measure of fusion performance that you can use across both measures comes from multiplying all three together. Well, the triple product achieved by NIF was higher than any tokamak, so that's one measure for success. But since you basically need the triple product to be extremely high, as you're only producing energy for a few milliseconds, and therefore the total power output has to be very large to get a decent amount of energy, it's not quite comparing apples with apples. And problems continued. Tiny specks of dust ruined some shots. Others were ruined by an unexpected problem. The target chamber is necessarily as close to a vacuum as you can get, all the air is pumped out, but it did contain small amounts of water vapour. These small droplets froze to the capsule and resulted in asymmetric implosions, so the whole RAM had to be redesigned to incorporate some tiny layers of glass. This essentially prevented the freezing problem from taking place. One of the issues with NIF is a familiar issue to anyone who's seen those Ghostbusters films. Don't cross the streams. If there's any interference between, or interaction between, adjacent laser beams, you're no longer getting the nice symmetrical irradiation you were hoping for. By 2011, the DOE overviewer was already telling the press that progress was not as fast as I'd hoped. However, the project still seemed to hang in the balance. As late as January 2012, the head of Laser Fusion Science at NIF, Mike Dunn, told a conference that we are now in a position to say, with some confidence, that we will achieve ignition in the next 6 to 18 months. And by July 5th, 2012, NIF had achieved its peak power shot, delivering 500 terawatts of power briefly to the target chamber. Unfortunately, that was also really the peak of NIF's ignition campaign. When it came time for a progress review towards ignition, published in mid-July 2012, the news was not altogether good. Quoting directly from that report, quote, "All observers note that the functionality of the laser, the quality of the diagnostics, optics and targets, and the operations by the NIC and NIF teams have been outstanding. By comparison with the startup of other large science facilities, the commissioning and startup of experimental operation on NIF has demonstrated an unprecedented level of quality and accomplishment, according to one reviewer. Experiments on capsule compression with improved diagnostic detail and exquisite laser pulse shape and energy control have provided important insights into the details of the compression of the capsule. The integrated conclusion based on this extensive period of experimentation, however, considerable hurdles must be overcome to reach ignition or the goal of observing unequivocal alpha heating. Indeed, the reviewers note that given the unknowns with the present semi-empirical approach, the probability of ignition before the end of December is extremely low, and even the goal of demonstrating unambiguous alpha heating is challenging." In other words, the NIF project wasn't failing because the people did a bad job. NIF's lasers themselves worked exactly as they were supposed to. It achieved all of their design specifications and was even capable of delivering more energy to the chamber than was initially planned. The experiments were running smoothly, and new laser fusion science was being discovered and analysed. But the results demonstrated that the device was still a considerable way off achieving ignition. The alpha heating referred to in the report was a key part of the mathematics of laser fusion, how laser fusion was supposed to work in the plasma physics simulations that were being run at the time. When you compress the capsule, you do produce fusion reactions. This has been true for a long time, and these deuterium-tritium fusions produce alpha particles, plus the famous neutrons. These alpha particles have a great deal of kinetic energy, and they slow down by colliding, primarily with hot electrons in the plasma. For fusion to work, you need these hot alpha particles to pass on their energy to the remaining unfused material, enough to push that fuel over the fusion threshold itself. That's what is really meant by ignition, and then a chain reaction can occur. The lasers provide the heating and compression and the spark, and then the alpha particles heat more and more of the fuel into fusion conditions. Then you can talk about the fuel pellet burning, ignition and sustained burn. So it's critical for the scientists at NIF to demonstrate that this is the process going on, and seek to change the experimental design to get as much alpha heating as possible so that they can have a more sustaining reaction. Instead, though, they found that they couldn't be sure, even at these pressures and temperatures, that alpha heating was occurring at all, in any significant degree. The report also expressed grave concerns about the theoretical and computational modelling, the code used to predict how the plasmas would behave. This really is a familiar story, as much the same thing happened with the NOVA device. In both cases, the simulations in advance had predicted that, well, if this device works, you'll be well within the range of energies and densities where ignition is expected to occur. Now, in both cases the devices had eventually worked, they had provided the correct amount of input power, but it just turned out not to be sufficient to allow for ignition to happen. Ultimately, a lot of the problems identified were the same old laser fusion issues. The lasers were interacting with the plasma produced when they collided with the target, which could lead to non-uniform irradiation of the target. The targets themselves didn't always implode with enough symmetry, and the scientists weren't sure if this was due to laser-plasma interactions or something wrong with the target design. The theoretical predictions had suggested that 30 to 40% of the kinetic energy dumped on the plasma target would be converted into heat energy in the fuel hotspot. Instead, it was more like 10%, which meant that the pressures that were being produced fell short of ignition pressure by a factor of 2 or 3. And the scientists at NIF, although they had designed an incredibly smooth target, still encountered Rayleigh-Taylor type instabilities which led to less compression. Remember, when you picture these, picture trying to squeeze a ball of jelly only to find big globs of it passing straight through your fingers and not getting crushed at all. Also, essentially the ablation material that they compressed the fuel with was mixing with the fuel, which was giving more uncertainty in the results, and this was difficult to account for in the computer code. So ultimately, the code and our understanding of the physics of how inertial confinement fusion would work was wrong, and the report noted that this meant they couldn't really use it to predict future experimental designs. That's why they talk about a semi-empirical approach. You're going into territory where you don't have many good theoretical expectations, so you just have to observe what you see and try and blindly optimise towards the best solution. Those behind the ignition campaign had hoped that, with a laser 10 times more powerful, it might just be a simple matter of making gradual, engineering tweaks to, say, the pulse of the laser, the shape of the laser, the capsule design, and so on. But instead it seemed like there was really a great deal more about the fundamental physics of plasma instabilities that needed to be understood. The scientists recommended new runs that weren't aimed at achieving ignition right away, but instead as diagnostic runs that would allow them to build up a better understanding of the physics of laser fusion. Of course, this means that in some sense, NIF is a successful science experiment. It's discovering and refining our understanding of how lasers and plasmas interact, and the next generation of theory and modelling of these devices will reflect that improved understanding. But NIF was almost sold as a prototype, the device that would achieve ignition, and there's no way around it. As of 2019, it has not done so, and those that work there are admitting it's likely that it never will. The report in 2012 said that while the data obtained didn't exclude the possibility of ignition, it remains a considerable technical challenge with an uncertain outcome. It was the first nail in the coffin for NIF's dreams of ignition. The US Congress was only willing to fund the pure ignition campaign until October 2012. After that, the lab's time would have to be increasingly shared between its weapons-related duties and further attempts at fusion. Laser fusion experiments at NIF have continued, and continue to this day. The immediate effect of their failure in 2012 was to refocus the efforts, not an engineering campaign that was close to ignition, but on a scientific campaign attempting to explain why it wasn't working. And improvements did arise from this approach. One notable set of pulses in 2014 produced a few more excitable headlines and some misleading ones. In 2014, a special kind of laser shape was used, in something the lasers called a high-foot laser pulse. This effectively involves hitting the laser with two pulses, an initial very sharp pulse, followed swiftly by a slightly smaller one. According to our best understanding of laser fusion physics, this sacrifices the maximum possible energy gain for a greater degree of control over the capsule's implosion. The aim here was to slow down the growth of those Rayleigh-Taylor instabilities, those tendrils of plasma exploding outwards that made symmetrical compression so difficult to obtain. What was good about this experiment was that the physicists were actually able to measure, with new diagnostics, how the Rayleigh-Taylor instabilities were growing, and they could confirm that the reason the ignition campaign shots had been unsuccessful was broadly because of these instabilities. The high-foot pulse that was used in 2014 reduced these instabilities, but revealed additional instabilities that we had suspected may exist, but were previously swamped by the Rayleigh-Taylor signal, according to another paper that was written there. So scientific progress was being made, but NIF, or perhaps the headline writers or the press release writers, were a little bit naughty in how they reported that scientific progress. They defined and reported on a new milestone, which was called fuel gain. They reported that their latest runs had demonstrated fuel gain of a factor around 1.2 to 1.9. What this means effectively is that the energy produced by fusion reactions in these runs was greater than the amount of energy that was deposited into the hotspot in the capsule during the actual implosion process itself. This is of course a notable achievement. It's something that no previous inertial confinement fusion experiment had achieved, and it was demonstrating that the alpha heating that was missing in 2012 has by now been observed at NIF. The plasma can be heated by its own thermonuclear reactions, but in some ways it's also an accountancy trick and it's a little bit confusing. The definition of ignition is that the fuel should be heated faster by fusion reactions than it's cooled by losses. So radiation, hot electrons carry energy away, plasma escapes carrying energy away, but you need the fuel to be heated faster than it's losing energy through those processes. Once the fusion reaction is ignited in this way, then you can take away the external laser and the pellet will continue to burn and produce fusion reactions and energy on its own. That's ignition. Meanwhile, the definition of break-even is a fusion reaction that releases as much energy through fusion reactions as is supplied to the fusion fuel. So what was achieved in 2014, while impressive, was not ignition or break-even. The energy that actually ends up getting supplied to the DT fuel is only a fraction of the energy that's deposited onto the capsule. Remember, other parts of it go into heating up the electrons or end up being radiated away. And this is only a fraction of the energy required to run the lasers. For example, we talked about how converting the laser's frequency already involves losses of around half the power that's supplied. The problem with fuel gain is that if you look at it quickly, or if you misreport it, you might think that they got more out than they put in, and that NIF therefore achieved its goal. The scientific paper describing these results did say in the first line that it wasn't ignition or break-even, but just because you say it in the first line of your paper doesn't mean anyone's going to read it. But this is not true. Ignition and break-even has not yet been achieved in any laser fusion experiment on Earth. The reason I'm being snarky about this is just to point out how far we still have to go. Even in the highest energy producing shot, the ratio of laser energy in to fusion energy out was less than 1%. Looking at ignition rather than break-even, experiments at NIF have pushed the plasma from achieving around 10% of the pressure needed for ignition to around 30% of that needed for ignition. So even NIF, which took over a decade to build and cost billions of dollars for all its scientific achievements, is a long way off achieving the goals of fusion, and it would probably take another generation device to get ignition or break-even. The problem with this kind of accountancy trick is that there are all kinds of different ways you can do the accountancy. My dear listeners, you've all been immersed in the world of fusion researchers and jargon for a long while now. Your innocence is lost. But to an ordinary person, if you're making a device that's supposed to solve all of our energy needs, it needs to produce more energy than it requires to run. Not more energy than eventually makes it to the capsule, not more energy than is used in heating the plasma, but more energy than its total use. Otherwise, it's just another way of spending energy. We talked about some of these problems in the Buzzkill episodes for tokamaks. Even once you have break-even, for economic engineering break-even, you have to convert that energy into electricity, where you'll probably lose at least 2/3 of it. You have to produce enough energy to cool down the magnets as well as heat the plasma in a tokamak. You have to produce enough energy to make up for the downtime for the reactor, and to take care of the air conditioning, and the vacuum pump and the general consumption from the whole power plant. There's a lot of losses and a lot to take away from the system before you can call it a power plant. And NIF suffers from similar problems. In the fuel gain shots, the lasers fired 1.8 million joules of energy at the whole round. The fusion pellet eventually absorbs just 12,000 joules of that energy, and it releases around 18,000 joules, which gives you a fuel gain of 1.5. So yeah, there's fuel gain. The fusion pellet absorbs 12,000 joules and you get 18,000 joules out of the fuel pellet. But if you look at the whole system, you're not gaining any energy at all. If you gave £1.8 million to your financial advisor, and they gave you £18,000 in return, explaining that yeah, they wasted most of it, but the $12,000 they did end up investing was performing really well, well, you might wish that you'd invested in solar panels instead. And of course, if you want to be a real buzzkill, it's even worse than that, because only a small amount of the energy required to operate NIF ends up concentrated in that laser pulse. To amplify the laser, you need to, amongst other things, charge that bank of capacitors in the amplifier. Remember the ones that occasionally used to explode? If you assume that the capacitors were fully charged for these shots, and that they dominate NIF's total energy usage, they store 422 megajoules of energy. So fuel gain is a very good scientific achievement, but if all you see is energy in minus energy out, you're really only getting out 0.004% of the energy you put in. How large does that number have to be before you can really call it a feasible power plant, let alone an economically competitive one, given that it costs billions of dollars to build? Some conceptual studies suggest that you might need to get a fusion gain of a factor of around 100 for the reactor to be economically viable. So you would need that to be 10,000% rather than 0.004%. NIF is a long way short of that. And in fact, a laser design like NIF could never achieve this because simply too much is wasted along the way. Some estimate that the maximum credible yield from a single shot at NIF to be around 45 megajoules, compared to the 400 odd megajoules required to fire the down laser in the first place. Ultimately, you would need to design a system with a lot fewer losses along the way. If you want to compare lasers and magnetic confinement fusion in another way, around 25% of the energy taken from the grid to power jet ends up heating the plasma, compared to maybe 0.00025% of the energy from the grid that's used to power NIF. So comparing inertial confinement fusion break-even with magnetic confinement fusion break-even isn't really fair. Break-even is Q equals 1. If jet runs at Q equals 4, then the plasma is releasing as much heat as the tokamak takes from the grid. If it runs at Q equals 20, it might be economically feasible. NIF would need to run at Q equals 40,000 to produce as much energy as it takes from the grid, and that's before all the losses in converting that energy back into electricity. So it's not really comparable. The reality is that you need either a much bigger laser producing much greater power from the target, or you need a different design. And remember the amount of practical burdens yet to overcome that laser fusion really hasn't even been able to think about yet, because they've been so busy trying to get it to work. Once you produce that energy, how do you capture it and harness it? How much heat generated by the fuel pellet can really be eventually captured and converted back into electricity? How are you going to fit an entire power plant on top of an incredibly large and delicate laser facility? And given that NIF is currently only firing a single shot a day while its components are allowed to cool down and the next shot is prepared, how much energy could you feasibly produce with this setup anyway? If your reactor can only fire once a day, you can hardly claim to be solving the intermittent supply problems associated with renewable energy. Let's imagine that you wanted to use a NIF-like design to achieve a power output of 500 megawatts. That's about the size of an ordinary power plant. That's about as much power as the ITER tokamak hopes to produce. How often would you have to fire the laser to produce 500 megawatts of power? Well, bear in mind that the peak that it's ever been able to fire at is around twice a day. Some conceptual designs for a NIF that would produce 500 megawatts of power would need to fire the lasers approximately 50 times per second. Now, I don't work on this stuff, I'm not a materials scientist, but the prospect of scaling this up to a point where you might call it a power plant just introduces so many issues. For a start, if the materials take hours to cool down before you can even think of another shot, how can you make optical crystals that won't take as long to cool down? Or do you have to cool them, thus expending more power to cool them down so that you can fire the laser again? Unlike, say, the first wall in ITER, which is already a huge material science challenge because it has to withstand neutron bombardment, you can't just make these amplifiers out of anything. They have to be made out of crystals that amplify lasers. So does such a material even exist? And if it doesn't, how often would it break under this kind of intense punishment? And how much downtime would your plant expect to have while you're replacing or cooling components? Then, of course, there's the ability to actually fire the laser that often. You're going to need to be able to supply power to the laser somehow. Can you charge up and discharge those capacitors 50 times a second, given that they sometimes explode in normal use? Given that they store megajoules of energy, charging them multiple times a second is going to require megawatts of power. you'll need a whole different power plant that's simply dedicated to producing energy to charge the lasers in your laser fusion power plant, which begs the question of whether it's really worth building the insanely complicated laser fusion power plant in the first place. How long does it actually take to charge and fire the laser pulse, and what's the minimum feasible time to do that in? In all honesty, it seems like a bloody difficult engineering challenge to actually position the capsule in the centre of the vacuum that the laser beam is pointing at 50 times a second. I mean, think how quickly you'd have to be replacing these capsules. So obviously there needs to be lots and lots of design changes before anything like NIF could ever produce any net power. And we've already seen that the tiniest possible grain of sand on the capsule, or the tiniest misalignment, means that the whole shot fails to produce any energy at all. And if you want to get into the economics of it, the real economics, those gold capsules and perfectly spherical fuel pellets don't come cheap. Some estimates suggest that they might need to cost 25 cents a piece for fusion energy to become economically feasible. They currently cost $25,000 to manufacture. Buying in bulk can only help you so much. So it's clear, even if NIF had achieved ignition, or you could make a really good case that its successor would achieve ignition, that's not where the problems end, that's where the problems start for laser fusion. Making laser fusion into a scientific reality is proving hard enough. We don't know for sure that it can even be done, but making it a commercial reality is truly mind-boggling. The scientists at NIF did briefly fund a project called LIFE, which was aimed at investigating the practicalities of harnessing fusion energy from NIF or its successors. But many pointed out, given how far NIF was from achieving ignition, the practicalities of a laser fusion reactor design were still a long way off, and evidently the design would have to be changed substantially before you could even think about it being practical, and the project was quietly dropped a few years ago. One of the more recent DOE reports was a little more stark about the prospects for NIF. The question is if the NIF will be able to reach ignition in its current configuration and not when it will occur, said the 2016 report. Computer codes and models predicting high energy gain from the fuel capsules were not capturing the necessary physics, wrote the review's authors. Experimental efforts were frustrated by the inability to distinguish key differences between laser shots, with similar setups producing scattered results. Most damningly, the review in 2016 cited a failed approach to scientific program management, based on circumventing problems rather than understanding and addressing them directly. Moreover, the report, while being clear that scientific progress has been made, implies that there's still a long way to go to understand the fiendishly complicated physics of laser-capsule interactions. The computer modelling and theory is still not up to scratch. It's still not considered to be sufficiently reliable to predict how a totally new design will behave. And so the report cautions that scientists must accept and prepare for the possibility that there is no existing experimental setup that will achieve ignition. Naturally, there is various associated sniping. Some people who predicted as far back as the early 1990s that NIF could not succeed have spent the best part of their careers saying the same thing. And there's disagreement about the scientific community about where to go next. Some think that the instabilities can be overcome by using bigger capsules, but these might in turn require a bigger laser to drive them. Others think that a new kind of laser, one based on krypton fluoride gas rather than solid crystals, will provide a smoother beam and a smoother route to ignition. Some experiments are considering using thin layers of diamond or beryllium, rather than plastic, as the outer layer of the capsule to help compress the fuel. Of course, NIF is far from the only inertial confinement fusion project out there, and far from the only large laser facility. There are dozens of other concepts and ideas that exist and are being tested throughout the world, and we might come back to some of them when we talk about modern-day startups that are trying to get fusion to work. Perhaps the route with most hype in recent years is something called fast ignition, which effectively separates the stages where the compression and heating occur. We talked about this a little bit when we discussed NOVA. First you compress the pellet with a long pulse of lasers, then when it's at its maximum density, you blast it with another ultra-high powerful laser that delivers a large amount of energy directly to the hotspot in the core. The idea is that this laser actually bores through the outer layers of plasma to the hot core, a technique referred to as plasma bore-through. There was considerable hype around this, especially because it gets you around some of the problems associated with making an indirect drive like NIF practical. After all, one of the problems with NIF is that only a tiny fraction of the laser energy is actually supplied to that central hotspot, which is why scientific break-even is so far from engineering break-even, and why you have to fire your laser fusion financial advisor. With this method, you would hope to pour a great deal of laser energy directly into the hotspot at its hottest, and thus, overall, reduce the power of the laser that's required. There were plans to build a big facility in the EU called HYPER that would perform this. Now, I had a look around, and it's actually really difficult to find out that much about the fate of HYPER, so if anyone knows more about this, please let me know. Get in touch on www.physicspodcast.com. I can find plenty of rusty old slideshows suggesting that it would have been built by 2015 that referred to the imminent ignition at NIF, so that's obviously not the plan anymore. The most recent document I could find was from 2014, where the report on the preparatory phase was still talking about NIF achieving ignition in a couple of years. As far as I can tell, HYPER still only exists as an idea, and has done for more than a decade now. People have talked about it, but I don't think it's been built. Although there are certainly people at laser facilities looking at fast ignition and other techniques. China, for example, has its own inertial confinement fusion facility going on at a particular laser facility, and a recent paper even claimed that they might achieve ignition by 2020, but honestly I think you'll agree by now we should believe that when we see it. There's also the Laser Megajoule facility in France, and scientists in Japan working on fast ignition techniques. Lots of the proponents of inertial confinement fusion suggest that we know it works because it works in nuclear bombs, and it worked in the underground Halite Centurion tests. One can apparently get energy out of a DT pellet in this way. But because those tests are classified, we just don't know what the lower threshold for ignition might be. The smallest yield bomb that was used was what set the lower threshold for the halite tests. Some suggest a laser 10 times the size of NIF might do it, others suggest 100 times. The results from Halite Centurion were obviously promising as the US began to focus on ICF, but they're classified, so how can we know if they're really close or if it's just wishful thinking? But I'm not sure what we've established yet is that this could even work on a scale much smaller than a nuclear bomb yet developed. There are lower limits to the yield of nuclear bombs that have been known about by weapons designers for a long time, beneath which it's just very difficult to get any kind of hydrogen bomb working. Overcoming these instabilities remains an extremely difficult challenge. Converting them into a practical power plant will require even higher energy gains if you need a 10 megajoule or 100 megajoule laser. In the 1970s and 1980s, when laser fusion was first introduced, it had appeared to be a shortcut to fusion, a faster, smarter route than all of this mucking around with tokamaks and magnetic fields. You just blast the capsule. Atomic bombs did it, so why wouldn't it work? And it was one enabled by the invention of a new technology in the laser, and since it had never been applied, people had a lot of reason to think that it might be easy. But like the magnetic confinement fusion teams before them, the laser fusion people found that plasmas were capable of behaving in strange and unpleasant ways, far more often than you might hope. Ultimately, the failure of NIF has likely proved very damaging for the future of inertial confinement fusion. The inertial confinement fusion efforts were mostly focused in the United States, as magnetic confinement was increasingly abandoned, and never had quite the same level of international collaboration as JET and ITER did. When you have one big, highly publicised experiment that's aiming to achieve a certain goal, and then it doesn't succeed, it's hard to see how that doesn't push the project back by decades. In my mind, the failure of NIF to achieve ignition is similar to what might happen if ITER failed to reach break-even, or perhaps what happened when JET failed to achieve break-even. It really has a massive chilling effect on the whole field, for new scientists, for established scientists, and for funding bodies. There are a great number of people doing excellent, groundbreaking work on laser fusion. I've met some of them, but it's clear that we still have an awfully long way to go. One huge project ultimately didn't succeed in its goal, and it will take decades until anyone will be willing or able to construct and or fund another one in the same field. I mean, JET started operations in 1984, and ITER might not start until 2025. So with the rate of funding and the way things are going for fusion at the moment, could be a gap that long even between big experiments for inertial confinement fusion. 40 years maybe. With so many technical challenges still to overcome, it's really difficult to see how anyone is going to be persuaded to build a laser that's 10 times bigger than NIF, at the cost of tens of billions of dollars. If inertial confinement fusion is going to work then, I think it will need some new unforeseen development or breakthrough, possibly using a quite different approach to that NIF has used so far. I wouldn't rule out such a breakthrough. It would be foolish to do that. We've seen all kinds of interesting things happen in plasma physics. But I wouldn't bet my life savings on it either. If nothing else, at least NIF can always boast that part of Star Trek Into Darkness was filmed there. The target chamber stood in for the warp core of the Starship Enterprise. As far as I can tell, here in 2019 as I write this, NIF still conducts inertial confinement fusion experiments, testing out different capsule designs and different laser parameters. But most of their recent output is on weapons testing and design. There's been some talk of trying to reconfigure NIF. Instead of blasting a target via a hole round, which is the metal container that produces the symmetric X-rays, blasting the target directly with direct drive. Direct drive has its advocates, and maybe some tests will be carried out using the NIF facility, but it's not what the laser was initially designed for. NIF's lasers were not designed to be perfectly spherically symmetric, but instead to uniformly illuminate the hole round, so a major configuration would be needed. And the best calculations available at the moment suggest that, in direct drive mode, the laser still might only get 50% of the way to ignition. Given that the indirect drive calculation suggested ignition was within reach, only to find that it was more like 10% of the way there, maybe the direct drive approach wouldn't get that far either. Some other more recent experiments have demonstrated that if you use liquid hydrogen, which can form a more perfect sphere in vacuum, filling in bumps and imperfections, surrounded by a thin layer of foam, and you turn the power of the laser way down so that instabilities are less excited, you can achieve higher pressures and densities than before. In other words, it's basically easier to achieve maximum compression with the laser turned up to 5 than it is to achieve half compression with the laser turned up to 11. It's not going to get them near the initial goal of ignition, but under these conditions, the plasma theory and modelling that exists works quite well, which means they can seek to optimise it some. So work done on inertial confinement fusion at NIF might still guide us towards inertial confinement fusion in the future. It's not a hopeless endeavour, but it's tricky to see funding for a NIF successor on the horizon anytime soon. More recently, NIF has also begun to rent itself out to various different groups of scientists with interest and access to the world's most powerful laser facility, for mysterious science under extreme conditions. There is some amazing science being done at NIF. I mean, it is the most powerful laser on the planet, capable of creating hot and dense conditions that can be found in few other places on Earth. One of the results that caught my eye was their use of NIF to compress hydrogen down to its metallic form and study its properties. And of course, we now have a greater understanding of the physics of laser fusion. The best science available when it was constructed suggested that it might work, and I'd always argue for spending on science, even the big flashy experiments, over plenty of other things that governments choose to spend their money on, like, for example, nuclear weapons. But it is unavoidable, inescapable to point out. NIF, the National Ignition Facility, failed to achieve ignition. It may leave behind a legacy of awesome science, and who knows, it may even be one of those stepping stones along the road to fusion in the future. But in its primary objective, it did not succeed. That too will always be part of its legacy. Next time then, we'll talk about the surviving major international fusion experiment. It's been a while on our show since the USSR and the USA agreed in principle to a huge international collaboration on the world's biggest tokamak, a truly global scientific endeavour with the aim of liberating nuclear fusion for the world. And still today, as I write this, the device is being constructed right now in the south of France, and still many are heralding and hyping it as the route towards finally making fusion power a reality. So, how's that working out? The next episodes of the show then will take us right up to the present day, and into the future. ITER, show us the way. Thank you for listening to this episode of Physical Attraction. As ever, you can find us on the web at www.physicspodcast.com, where you'll find the contact form, the PayPal and the Patreon, all ways that you can get in touch or help support the show. You can also support the show by telling as many other people about it as possible. Every little helps to get more audience. Until next time then, take care.